Need to share the screen again. Alright, can you see the DocuCam now? Yes, okay, alright. So we looked at this problem. So we are in a situation in which we have a mass that is on an inclined surface of 30 degrees. We have an external force applied, is a force that changes in time. We have 90 sine of 2.5 t. And then we also have the value of the elastic constant, which is 1000 Newton per meters, and then we have the value of the mass, which is 50 kilograms. We also know that this is initially at rest, and we have to find the equation of motion and the response of the system. How do we do that? Any suggestion? We have to do the summation of forces. I agree with you. So where do we start from? We start from the free body diagram, right? So we start from the free body diagram, which means we look at all the forces that are applied on our body. So our body looks like this. So what are the forces that are applied on our body? We have the spring force, which is so I would start from the external force, because when we look at the external force in this exact configuration, the external force is in this direction. We can call this F of t. Of course, we also have the spring force that is on the other side and is also opposite, in the opposite direction, because if the force of the spring is pulling the mass in this direction, it means that we are stretching the spring, which means that the force is trying to pull the mass back. So this is the Fk. We can call this Fk. Anything else? We also have the gravity. In previous cases, we had the mass in the horizontal direction, moving in the horizontal direction, so the gravity, the force of gravity was completely balanced by the normal force. This is not the case anymore, because now we have only one component. So here mg. So now that we have the forces, theoretically we would have also the normal force that is perpendicular to this inclined surface. However, since we don't have motion in the direction perpendicular to the surface, we are not really worried about that one. We need to look only at the forces that are in the horizontal direction. And we have all of them, because we have the force from the spring, the force from the external force, and then we also have the gravity, which will have a certain component in the horizontal direction. So now that we have these forces, we can finally write our equilibrium equation. We always start from summation of forces in the x, we call this like x direction, equal to m x double dot, which means that we have F of t, so the external force, minus the force of the spring, Fk, and then of course again we have the component, the component of the force of gravity in the same direction of the motion, so this will be mg. It is in the same direction also of the external force, so we have a positive sign, m times g times sine of the angle theta, because again we're looking at this component here, and this will be equal to m x double dot. Again, we called x the direction parallel to the surface of this plane. So now we have to plug the force of the spring. So the force of the spring is the elastic constant multiplied by the displacement, of course we have, since we have the force of gravity to extend the spring, we will have a certain static component and a dynamic component. So we can write the force of the spring as K times, we can call it X, which is the changing displacement, plus delta, which would be the static displacement. So since we have this here, and we also know the external force, we can rewrite our equation of motion as m x double dot minus mg sine of theta plus k x plus delta equal to 90 sine of 2.5 t, which is what we have here. What should we do next? Is this a form that we are familiar to, or not really? So for sure we can divide by the mass, because here we have the mass, here we have the mass, here we have k, we divided by the mass, and then we can look at the natural frequency. However, I think before doing that, we should slightly simplify this equation. What should we look at to simplify this equation? Like this delta, we multiply by k. So that's correct. We can look at the product between this k and delta. Why do we need to look at this product between k and delta? Because actually what we should do now, we should look at the static deflection of the spring. Basically we have to look at the static equilibrium that occurs between the force of the spring and the component of the gravity in the direction of the motion. So if we look at the static equilibrium, the only two forces, static equilibrium means that we don't have this force, because again, for the static equilibrium, this force is not involved because this changes in time. So for the static equilibrium, we need to look at the force of the spring with its own static deflection and the component of the gravity in this direction as well. So when we look at these two forces, we simply have that mg that multiplies sine of theta minus k delta would be equal to 0, which means that mg sine of theta is equal to k delta, because again we're looking at these two forces here. They balance each other, again in a static condition. So since they balance each other, it means they are equal. If they are equal to each other, we can simplify this expression here, because we can get rid of this mg sine theta and then this k delta here. So once we do this one, our equation becomes, the dynamic equation becomes mx double dot plus kx equal to 90 sine of 2.5t. Now we can go through the step that we mentioned before. We can divide by the mass so that we can obtain the standard form, and then for now we are going to use these two, like 90 and 2.5, like symbolic, so that it's easier to handle. So when we do this, we will have the standard form, which will be x double dot plus we can do omega n square x equal to our lowercase f0 sine of omega t, where lowercase f0 would be 90 divided by the mass, the 50, and this omega would be 2.5. So this is the standard form of the equation of motion. What do we do with this? Okay, we have to find some solution of this equation, but the standard form that we have is second derivative of the function plus omega n squared times the function, and then equal to the external force. We already have the solution to this one, right? What do you think? Do we have or we don't? Well, what we need to do, so we have something similar to this. As Vasan said, we have something similar, but we don't have the exact, we don't have the solution to this exact equation. Because if you remember, when we were looking at the first example, we had that the external force was F0 cosine of omega t. From this external force, we obtained this standard form of the equation of motion, which means x double dot plus omega n square x equal to F0 cosine of omega t. Which means that this solution that we found is not applicable anymore to this case here, because in this case the external force, which is responsible of the non-homogeneous term of the equation, is actually F0 sine of omega t instead of being F0 cosine of omega t. Make sense? Any question about this? So we don't have the solution to this one, which means that we have to find the solution. Now the steps that we should follow are exactly the same steps that we followed before when we were looking at the solution of the equation with F0 cosine of omega t. So I'm not going to write them down all of them, but just I will try to summarize them. So the first thing that we should look at is the particular solution. So the particular solution can be written in the form like b sine of omega t. If you remember in the previous case, the form of the particular solution was a certain amplitude. Here we called it x. In this case we are calling it b, but of course the meaning is the same, times cosine of omega t. Basically this is because here in this case, for our new external force with the sine, we are going to call this, we are going to have this particular solution, b sine of omega t. This is because also has like a physical meaning, and this is because when we apply a certain external force to a system, basically the solution will be composed by these two components. One would be again the homogeneous, one would be the particular. The homogeneous solution is typically corresponds to the transient portion of the solution, and then the solution of the particular the particular solution corresponds to the steady state. So when we look at the entire timeline, there will be like a first portion that is like again the transient, and then there will be the second portion, which is the steady state. So the transient is typically influenced by the initial conditions, because depending on what type of initial velocity you have or what type of initial displacement that you have, that will be the very first portion of your response. But then you have the second part, which is again the steady state portion of the solution, and that is mostly influenced by the external force. Makes sense? So this is why when we have an external force that looks like this, F0 cosine of omega t, we assume that the particular solution has this form here, with the cosine of omega t. When we have an external force that looks like this, with the sine of a certain omega t, we assume that the particular solution also looks like b, a certain amplitude, sine of omega t. Does it make sense? Okay, now we have the last 5 minutes. I'm just going to summarize what we should do for this type of problem. As I mentioned already in another lecture, I think it will be actually a very good practice for you to go through the steps, the derivation of the different functions, and then find the final solution. So again, the first step is to set the particular solution. Then once we have the particular solution, we can calculate the first derivative. Then we can calculate the second derivative. And again, you can go through these actual calculations. So once you have the first and the second derivative, we can plug them in the equation of motion. So we'll have our x particular of t plus omega n square that multiplies the, excuse me, this is second derivative, this is the function, equal to f0 times sine of omega t. So we have the particular solution, we calculate the first derivative, second derivative, we plug the function here, the second derivative here, equal to f0 sine of omega t. And then from this one we can find b, which is basically what we have here. And what we should find is that b is equal to f0 divided by omega n square minus omega square. Actually, so far very similar to what we had before. Which means that xp of t would be this quantity here times sine of omega t. Then once you have the particular solution, we can look at the total solution that we call as xt, and even in this case we have the solution to the homogeneous with a1 sine of omega n t plus a2 cosine omega n t plus this quantity here, which is f0 divided by omega n square minus omega square times sine of omega t. And then once we have this one, we can use the initial conditions. Initial conditions means initial position and initial velocity, which means that we plug 0 here, and then we equate this one to x0, then we calculate the first derivative, and we equate that first derivative to v0, where t is equal to 0, and then we finally find, the two constants a1 and a2. Once we find a1 and a2, we can plug them here and here, and then we will have the total solution. Now, with the numbers that we have from our problem, So the numbers that we have here, the solution would be like this. So in this case, the solution would be negative 0.0732 sine of 4.472t plus 0.1309 sine of 2.5t. So again, this is the final solution. There are all the steps in between. So I would strongly suggest to go over these steps to make some practice, because I think it would be useful to have a better understanding of the concepts. Any question? So if there are no questions, we are done for today, and next time we will start to talk about damped forced systems. Alright? So have a good night everybody, and we are going to meet in a couple of days. Thank you.